Hello, happy Monday or Tuesday or whenever you're watching this. Um, so last class we did the projectile motion, the vector displacement lab. Sorry, I said projectile motion. We're doing that today. So you guys did the vector displacement lab last class. So you were solving those vectors algebraically using your trig functions and the Pythagorean theorem. And for any of your non-perpendicular angles, so if you had angles that give you like many vectors put together, or you had like an obtuse angle or something, you were using the component vectors to solve for that. So you could have used like the law of sines and law of cosines to solve for those, but the component vectors was the goal because we're going to use those for projectile motion. So today we're going to start on projectile motion. Kind of our goals for today is to recognize examples of that, describe the path of a projectile as a parabola, and then to resolve your vectors into components and apply some of these kinematic equations to solve your problems. So some of these equations will be familiar. We've used them slightly different variations of them already this year. So with two-dimensional motion, just a reminder that our vectors can be resolved into individual components, okay? So if you're looking at this, you could, if you're trying to find this point right here, this third one down, I guess, you could resolve it into its vertical and horizontal components to solve and then calculate your angle. Just in general, your projectile is going to be an object moving on a curved path until it reaches its point. So the projectile is the object that's being moved throughout space. The trajectory is the path that the projectile takes. So you kind of have three words to describe these, and they're not the same thing. So projectile is the thing that is moving. So like in this case, a cannonball is the projectile. It's moving on its trajectory, which is its path, and then it would form a parabola, or in this case, half of a parabola because it starts at the peak on a graph. So when we try to solve for projectile motion, using the components is going to simplify things. So you always want to think of any object as having both an x and y component. So if you look at this chart here, it shows, very clearly all these lines are showing your difference between your x and your y. So you have this little green arrow showing your horizontal motion versus your red arrow is your vertical motion. And it makes sense if you look at it based off of, based off of the magnitude of these lines, because we would know that if we were talking about just force in general, I guess we could talk about velocity here because it has velocity listed. Initially, your horizontal velocity would be very low because it's mostly like if you toss the ball straight up in the air, most of your velocity is moving upward. And as you start reaching the peak, you get smaller and more equal as you move. Then at the very peak, you have no more upward motion. So the upward motion would be zero and you have a small amount of horizontal motion. Then it starts to fall again and you'll see these arrows kind of switch places and increase again. So we can easily break all of these down into their horizontal and vertical components to solve for different points of a projectile. So other examples of projectiles would be just anything that's being like launched or thrown. So throwing a softball, basketball, shooting an arrow, anybody like long jumping, things like that. So as I was talking about earlier, your parabolas, projectiles follow parabolic trajectories. So this is helpful to us, especially in physics. And at this point in physics, we are ignoring air resistance. So you should have nice parabolas on all of your problems. So for our purposes, we're going to consider horizontal velocity to be constant unless it says otherwise. We do know that air resistance can affect horizontal velocity, but we are, that's not part of our curriculum in high school. But we know that we could include air resistance and that might change the shape. So before we get started with any formulas, I just wanted to bring up like a reminder slide of all the variables that are involved. So we know that v is velocity, We know that t is time, a is acceleration. We've been using those for a long time now. If it has a subscript of 1 or 2, that's talking about if it's the initial value or the final value. We know that gravity is going to be negative 9.8 meters per second squared. So in all of our projectile motion problems, gravity, which is acceleration, will be negative 9.8 because gravity is always pulling downward. So we are initially launching or throwing the objects upward first, or they have some sort of horizontal motion first. So gravity will always be negative for these. Some things we haven't really used a lot yet is including y and x. So if something has a subscript of x or y, that is just indicating that you're talking about your vertical versus horizontal motion. And then here in blue in the center, D, we've been using D for displacement or distance. And in these problems, it's going to be replaced by a delta Y or a delta X. So that's going to differentiate between your horizontal and vertical motion. So a lot of these formulas will be familiar, but you will have been using D this whole time, and we're just replacing that with delta Y and delta X to show vertical versus horizontal motion. So projectile motion is basically just a free fall with some sort of initial horizontal velocity. Okay, so these formulas here are going to be specifically for projectiles that fall from rest or start at rest. So if I kicked a rock off the side of a cliff and goes straight down, you shoot a bow and arrow, you shoot a bow, it goes straight and then falls. So this type of projectile has both horizontal and vertical displacement. So remember that gravity is going to be negative 9.81, and then when it's falling, delta y, so your vertical distance will be negative because it's going downward. Okay, so keep that in mind. So if it's on its initial way up to the peak, that vertical distance will be positive, and if it's on its way back down, it'll be negative. So we do have 3 formulas here. This first one's just basically speaking is velocity is equal to acceleration times time, or the change in time. Then we have velocity squared is equal to 2 times acceleration times the change in vertical distance. Then we have the vertical distance is equal to 1/2 times acceleration times time squared. So hopefully these look familiar to you. They should. Initial velocity is involved in here somewhere, but it's been removed from these because these are specifically talking about projectiles starting from rest. So all of these, it would be like v plus or minus the rest of this, and they're just removed because if it's times 0, it's nothing anyway. So these are kind of condensed, I guess. So when you look at these, you'll notice the subscripts of y, 2, and 1. So this is talking about specifically the velocity, the vertical velocity, vertical final velocity. Okay, so we have v, and then we have 2, and then y. So here you have acceleration. So this is your initial vertical acceleration, which still will be gravity. Down here you have your final vertical velocity. Okay, so just be paying attention to like x and y because that's giving you your different axes. So to continue this, you're still going to have some of these familiar formulas here. So this formula in particular, the horizontal motion of a projectile. So again, delta x is going to be your change in displacement or your change in position. So we're going to have the delta x is equal to velocity of x times the change in time. So to find the velocity of a projectile at any point during its flight, you need to find the vector that has the known components. Okay. So horizontal motion is going to be independent of vertical motion. You'll solve these separately. Then we know that we can use the Pythagorean theorem to find the magnitude of the line, and then trig functions to find just direction of the velocity. And so something that's a little different here than what we've been talking about. If you look at like this one in particular, so you have your x motion, you have your y motion, and then you have this vector like sticking out in the middle. This is the resultant vector, and since we're showing motion, all we have done is taken the magnitude of this line that would have been the hypotenuse and put it here. Okay, so we'll talk about that as we start solving them. So here are some examples of projectiles that are launched horizontally. So these are things that are starting at like the peak of the parabola, and they're being like tossed off the edge of something and falling. So this example, the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a rock horizontally off the bridge. The magnitude of the rock's horizontal displacement is 45 meters. Find the speed at which the rock was kicked. So find the speed that the rock was kicked. That's your initial velocity. So that's what we're trying to find. So we know that the initial speed will be horizontal because you kicked it. So some other information we have from this, we know that the distance, the vertical distance is 321 meters. So that is going to be our delta y. We know that it's falling, so it's going to be a negative 321 meters. So delta y, like it says right here, is negative 321. It says that the rock's horizontal displacement, which horizontal we know is going to be x, is 45 meters. So we'll put that there. And then we know that gravity is always going to be negative 9.81. So we're trying to find the velocity of x, so the velocity of the horizontal movement. So some things that we have here, let me let this menu drop, sorry. So we have this first formula is going to be the delta x is equal to the horizontal velocity multiplied with time. And then we also have another formula of delta y is equal to 1/2 acceleration times time squared. So we're going to have to figure out how we're going to solve for that. So you do have the option of plugging some things in here first. So we know that in order to solve for velocity, the Vx, because that's what we need Vx. In order to solve Vx, we have to have the horizontal displacement and the time. We don't have the time. So we're going to use the other formula first to solve for time. Now, if you really wanted to, you could take this second formula and you could rearrange this first formula and combine these two. So you could insert, like where it says delta time here, you could rearrange this so that it's equal to all of this and put that here, like you replace it and just have one formula to work with. That's fine if you would like to do it that way, but sometimes this way is a little bit easier not to lose track of pieces. So for these, we're going to solve for time first and then use the time and insert it into the second formula. So here we're going to have our vertical distance, which is negative 321 meters, equal to 1/2 times acceleration times time squared. Okay, so we just solve this algebraically, make sure you get the square root. So time is going to be 8.1 seconds. So it takes 8.1 seconds for the rock to go from the top of the bridge down to the river. Now we can plug that in here. So we have our horizontal distance is 45 meters equal to Vx, which is what we're trying to find, multiplied with the time. So this problem is telling us that our initial velocity, our initial horizontal velocity is going to be 5.6 meters per second. So just another example here, if you want to pause this for a second and try it yourself. Okay, so this one, a basketball rolls off of a 0.70 meter high desk and strikes the floor 0.25 meters away from the base of the desk. How fast was the ball rolling? Okay, so things we know. If you look in that box, we know the vertical distance or the change in distance for vertical was negative 0.7 meters because it's falling down. And then we're starting kind of at the peak of that parabola, if you will. And then the horizontal distance is 0.25 meters. It gives us all of this in the problem, and we know that acceleration is negative 9.81. What we don't know, we want to know how fast was the ball rolling. So again, we want to know the horizontal velocity. And I mentioned it before, but we're assuming that the horizontal velocity is going to be the same at any point right now. So some formulas we do have, if you go back and look at that list, we have delta x is equal to velocity times time, and then we again have the delta y is equal to 1/2 acceleration times time squared. So same formulas. We're just trying it from a different angle here. So again, we know we want to solve for Vx, so we have to have delta x and time. We do have delta x, but we don't have time, so we're going to use the other formula to solve for time first because we do have all of those variables. So if we start plugging these in, oh, this did not show all the steps, sorry. So if we plugged all these in, let that menu fall again. If you look at the bottom formula, the delta y formula, you would plug that in there. You'd have negative 0.70 equal to 1/2 times negative 9.81 times t squared. You would solve for t, and then you would plug that into the delta x formula to solve for Vx. So in the end, you would have ended up with 0.66 meters per second. So again, we can use our components to analyze objects that are launched at an angle. So before we were talking about objects that were launched basically from somewhere up high that were falling. These formulas are going to be used to solve for things that are launched like upward, like our rockets will be. Okay, so to analyze the motion of a projectile, again, we're going to have to resolve the vector into its components. Okay, so we already know about trig functions. You can use sine and cosine to find your horizontal and vertical components of the initial velocity. So you guys, I know, just use like SOHCAHTOA and you remember it that way and you kind of can visualize what you're looking at here with these. But this is laid out in a formula for you if that's helpful. So if you're trying to find the initial velocity of the horizontal motion, you could use this formula. So you would have the velocity, the initial velocity, or your V1 here, which is would have been solved for using Pythagorean theorem. So you'll have V1, then you have cosine theta. Same thing here for your Vy. You'll just use sine because if you're using it, looking for a different side, you would use a different trig function. So when you guys are finding these, and let's say you need to find V1, you would first need to use the Pythagorean theorem with these like light purple sides or these pinky sides. So you would have numbers in here. You would have to use Pythagorean theorem to solve for side C. So side C is this, okay, this dark purple here. This is called our resultant vector, and our vectors will look like this in our force unit as well. So basically what we've done here is figured out the magnitude of the line. So let's say two people were running perpendicularly. One person was running a little bit slower and one person was running a little bit faster. And you guys had like a string you were holding between the two of you with a ball in the center. So imagine that, like there's a really long string and you and somebody else take off running like north and east. Where would that string travel? Okay, like where would the ball end up if that was on the string? So it would end up right here. The two like forces added together in these two different directions gives you this resultant. So we're getting V1, which is the hypotenuse of this angle. And then you can solve for the angle that was created so you know what angle to draw this line at using your trig functions. Okay, so here are some formulas for you. Again, it's kind of this a lot of the same setup we've used throughout. So it's just using maybe some different looking variables this time around. So we have horizontal velocity. We're looking at the initial velocity cosine theta. We have the horizontal distance can be solved this way. The final velocity, the final vertical velocity can be solved this way. You just have a variation of different formulas they can use. And again, they're all using kind of the same components that we've been looking at all year. So they all have velocity, they all have displacement and time and acceleration. So those are your basic kinematics formulas that we've been using. We're just now like adding in angles and taking into consideration like launching and dropping. So here's some examples. So you have a baseball thrown at an angle of 25 degrees relative to the ground at a speed of 23 meters per second. If the ball was caught 42 meters from the thrower, how long was it in the air? Okay, so we're throwing it at an angle of 25 degrees relative to the ground. So we know that the get a pen here. So if the ground's here, oh, that's pretty. We're saying that the baseball's thrown here. Okay, so we have an angle of something we don't know yet. That wasn't pretty. But we know that the ball is going to keep going, right? And then somebody over here is going to catch the ball. He's going to be like excited, right? So what we know is we know that the angle is 25 degrees. We know the horizontal distance of 42 meters because the guy is 42 meters away. Gravity is always negative 9.81, and then the initial velocity was 23 meters per second. We're trying to find out how long was it in the air, so that's time. So how many seconds was this ball in the air? So if we go back to the previous page and look at this, it'll show us our formulas. Oh, well, I need to erase all this, sorry. So let's erase this bad boy. Our excited guy is gone. So based off of what we know we're going to have to find delta x. We have, so if we look, whoopsie, sorry, we're finding delta t on this one. I jumped too many. So we're trying to find delta t. So delta t is in almost every single one, right? So except for this one. So if we look at these 4 formulas and kind of narrow it down to what we have and what we don't have, you're going to end up using this one. Okay, so oops. Did it again. So you're going to use this delta x formula. We know the initial velocity, we know the angle, we're trying to find the time. So we're going to plug in for that and solve that for our missing variable. So we'll plug in our horizontal distance of 42 meters. We have the initial velocity of 23 times cosine 25 degrees times time. So then we'll just break this down and solve for it. So in the end, we end up with 2.02 seconds. And if you wanted to put this into correct sig figs, we would have to bring it all the way down just to 2 seconds, like 2.0, because of this 25. So another one, if you guys want to try this one out and pause it for a second. Okay, so for this one, we have a scared kangaroo. He clears the fence by jumping at a speed of 8.42 meters at an angle of 55.2 degrees with respect to the ground. If the jump lasted 1.40 seconds, what was the kangaroo's displacement? Okay, so for this one, okay, so again, here's the ground. We have a fence, and the kangaroo's like hopping over it. Okay, so the kangaroo's hopping over. We want to find what was his horizontal displacement. Okay, so we're not sure about that. We know that his V1, his initial velocity was 8.42. We know that the angle here was 55.2, and the time was 1.40 seconds. So let's erase this so we can work on it. I wish I could erase all of it at one time. Okay, so we have what we know listed over here. What we don't know, his horizontal displacement. So again, we're going to choose the formula that is going to give us what we need based off of what we have. So you do have so many formulas to choose from. And the best way to narrow that down is to identify which variable you're looking for and make sure that that variable is even in your formula. And then start looking for what else is in that formula and if you have it or not. So, of course, you can only have one missing variable to use a formula to solve for something. So it's just a matter of process of elimination. So for this one, we're going to use our delta x formula. So we'll plug in for this. So we have our initial velocity times cosine angle times the time. Okay, so this gives us a horizontal distance of 6.72 meters. And that's the end for today. Okay, so that was a little bit shorter, I think, than other lessons have been. I don't think that this is super difficult, but it can be tedious just getting through the formulas and making sure not to lose anything anywhere. Some things to remember is that acceleration should always be negative 9.81 and that you can use multiple formulas if you need to. Okay, so if you're missing one variable and you have the variables to solve for something else, you can use another formula first to solve for like time, like the example we use, you can solve for something and then plug that value into the other formula to solve for your final answer. So if that is the case, just make sure that you finish that up and you don't leave it at the first step. Basically, so just make sure you're always answering the question for what it's asking. So if you have any questions, please let me know. Otherwise, you can find your assignment on Canvas under the assignment tab. So I will talk to you guys later.